So first of all, there are a wide range of environmental interfaces. There's particulate matter in air and the surface of those particles in air. There's minerals in groundwater and the interface between those solid minerals and the water, aqueous water system above it. These interfaces impact things like air quality. They impact water quality. They can actually impact climate because particles nucleate clouds. They impact the ozone layer. So there are a wide range of environmental interfaces, and they have very important impacts on human health, ecosystem health, as well as planetary health. In our work on atmospheric aerosols, we've really developed a conceptual framework for understanding the chemistry of different types of aerosols, such as mineral dust aerosol. There's a lot of dust in the atmosphere. Planet Earth has a lot of desert regions, arid regions, which could become even more due to climate change. The dust gets in the atmosphere and it's transported many miles away. And so it really can impact the particulate matter loading in the atmosphere. We've looked at how reactions on the surface of those particles can change the composition of the particles. And so there's a lot of implications to the chemistry. You know, if you think about vibrational spectroscopy, it probes individual molecules and moieties, ions, and you have these spectral characteristics that are well known, but you put that molecule or ion in these different environments and their vibrational spectra change some. And by changing some, it tells us something about the local, I talk about the bigger environment, but this local molecular environment that actually plays a role in its reactivity, how it behaves, absorbs light, even solar radiation. And so we've utilized these techniques, a variety of them under this umbrella of vibrational spectroscopy as a way to probe these environmental interfaces. There's a hypothesis out there that if DNA sticks to surfaces in the environment, it will protect it from undergoing any degradation. So when I think about that problem, I think about there are a myriad of surfaces in the environment. Are they going to all behave like that? And so we just started some work looking at DNA adsorbed onto mineral oxide surfaces and determining whether its structure stays intact. The B form is the typical form. It has a certain handedness, it has a certain structure. And what we've learned so far is that it really depends on the mineral, what DNA is doing, what its structure is on the surface, and we use spectroscopy as a probe of that. And so that's been a recent exciting result of ours that we really want to get in the literature soon, and we're just writing up some of our initial papers